Hello, today I'm going to be showing you this 4-axis wire EDM machine that I 3D printed. Wire EDM, or electrical discharge machining, is a process that allows you to slice through anything electrically conductive using just electricity. It can cut aluminum, titanium, stainless steel, hardened steel, tungsten carbide, tungsten, graphite, conductive ceramic, and some carbon fiber composites. Wire EDM is a fantastically rare technology, which is unfortunate because it's excellent for rapid prototyping. There may only be a few thousand wire EDM machines left in the entire United States. That's why we're working in collaboration with LDO Motors to turn this into an open source kit, which you can pre-order using the link in the description. So you'll be able to 3D print the parts for this at home and build this machine in your garage. Okay, so let's talk a little bit about how all of this works. The most challenging part about building an EDM machine is the EDM power supply. EDM power supplies are esoteric and expensive. The EDM power supply is what creates the sparks necessary to do the cutting. In the past, if you wanted to purchase a power supply for EDM, it would cost you at least $3,000 to $4,000. That's where the Powercore comes in. The Powercore is the world's most affordable and most compact wire EDM power supply. It's also open source, meaning that you can hack it if you so desire. Right now, this is available for sale on our website. It'll run you about $400, and we plan to start shipping units out at the end of the month. Around the same time, we'll be publishing the source on GitHub. Normally, you'd plug in your wire EDM machine, but first we're going to do a demo by hand. To enable the Powercore, I'm going to be using the same enable we'll use for the wire EDM machine. What I have here is just a thin piece of aluminum for our demo. The positive 65-volt cable is connected to the work. To ground is connected a brass rod. This will be our electrode that we'll use to do the cutting. Finally, we need to add water. Our water is our dielectric. It's going to cool the metal particles that come off of the cut, in addition to providing a consistent environment for dielectric breakdown to occur. This is just regular store-bought distilled water. So this entire wire EDM machine uses Clipper, meaning that we can control it over a wireless network. Right now I'm controlling the EDM machine using my iPad. I'll press a button and enable the Powercore. So right now, 5 volts DC is being sent to the Powercore, and we are telling the Powercore that we are ready to begin cutting. Let's see what happens if we bring the electrodes together. So what's happening is that the Powercore is supplying short pulses of 65-volt DC electricity, and these are extremely high current pulses. What's interesting, though, is that if I were to put my hand in the circuit, because the Powercore is expecting a 1 ohm resistance, not a 1 mega ohm resistance, very little current actually flows. I can feel a slight tingle on my hand, but it's almost nothing. Now, we don't recommend you do this, but it is interesting to note that if you were to stick your hand into a wire EDM machine, you would not lose your hand. Compare that to a regular CNC mill. If you were to stick your hand into a CNC mill while it was running, it would rip your hand off, it would mutilate you, it would break your bones. It would not be a good time. One thing you may notice is that this brass rod is actually being worn away while we're cutting. This is called tool wear, and it's undesirable. Now, tool wear becomes a non-trivial concern when you talk about processing much larger amounts of material. This is 3/4 inch thick 6061 aluminum, and if we were to sail this brass electrode right on through here, it would not get very far at all until most of it had been used up and we didn't have any more electrode to cut with. So what we really need is a method to replace our electrode as we're doing our cut, thus wire EDM. In wire EDM, the electrode is pulled through the material so that it is never used up and we always have fresh brass to cut with. And using this method, we're able to get fantastic accuracy. So what I'm going to do next is hold the brass wire in my hand and keep it under tension, and then we're going to bring it to the material and see what happens. The Powercore pulse generator itself is able to remove material with micron precision. So the tolerances achievable are essentially dependent on how well tuned and calibrated the CNC machine steering the brass wire is. All the Betta wire does is robotically move the brass wire around. We just need to feed it stock material, water, and G-code. I'm securing in 1/2 inch 6061 aluminum bar stock into the onboard wire EDM vise. This vise is connected to the positive side of the power core. As the brass wire is consumed, it becomes yellower due to the outer protective coating of zinc being ablated away. It takes 5 minutes to cut down the bar stock. Afterwards, I face the remaining material with a 2.5 mm per minute skim pass. Over the next hour, the Betta wire completely fabricates our part. Waste slugs drop automatically as the 100 psi water jet pushes them out of the way. For years, I've wanted a machine like this. As a hardware developer, my greatest source of frustration is having to wait weeks for sample parts to be fabricated and shipped to me. Recently, I submitted a quote for a customized aluminum extrusion heatsink. The lead time was at least 6 weeks from a shop down the road. Thankfully, now with desktop wire EDM, I can make a prototype in hours, not months. It is worth mentioning that the cost of ordering a wire EDM cut part may be greater than the entire cost of building this kit. The tolerances achievable are similar to a common desktop 3D printer. On revision A, we can hit plus or minus 100 microns. On the next revision of this machine, we are targeting 50 micron tolerances. This transformation could be achieved with a more robust gantry and improved toolhead design. It is exciting to consider how the landscape of rapid prototyping could change with the introduction of affordable, moderately precise wire EDM technology. Given the characteristics of EDM, the surface finish of the parts is exceptional. Aluminum components, in particular, exhibit a sparkling appearance when illuminated under bright light. In this revision, both the top tool head and the wire spools can be detached by undoing just a single fastener each. The top tool head is tasked with pulling the wire onto a waste spool, while the bottom tool head employs a miniature friction brake pad to maintain tension on the wire. Most of the improvements I want to make before our official release are to the tool heads. This is a 4-axis wire EDM machine, which allows the top and bottom tool heads to move independently. This capability enables the cutting of tapers and chamfers. This is achieved by stacking 2 Core XY motion systems, one for the top gantry and another for the bottom. Each system is equipped with its own motors, idlers, and belt tensioners. This scheme permits high-density packing of mechanical components, which is essential because the entire device must fit inside a 10-gallon aquarium. Waterproof motors are more expensive than the regular variety, so to save resources, all of the motors are located above the water line in a special compartment. The bottom gantry motors are connected to the pulleys below them with a long stainless steel rod, kept in place with bearings. The control electronics are secluded on the back of the machine. Removing the magnetic panels allows the operator to easily service the device. Inside is a 24-volt switch mode power supply and a Manta M5P control board. There is a single board computer which runs Clipper firmware. I am only using 4 of the 5 motor drivers, so there's room for an additional rotary axis in the future. Wire harnesses are captured with waterproof cable glands. The harness I am currently removing supplies 24 volts to the wire spool motor. There is an additional via for LED lights and the Powercore enable. Another harness connects the Powercore anode to the stainless steel precision vise. One aspect of this revision that I am proud of is the minimal use of fasteners. Fasteners are good at providing a preload, but are poor at aligning components. Fasteners require time to screw and unscrew. A threaded insert or nut is often required for each fastener. To combat fastener bloat, I made liberal use of stainless steel precision pins. Pins can be easily pressed into a part by hand. By using this approach, I was able to decrease the number of fasteners on this machine by 75%. Removing this entire assembly required me to unscrew only 6 M3 fasteners. By using fewer fasteners, I am free to select high-quality countersunk A2 steel metric hardware from reputable suppliers. This assembly is a spacer between the aquarium wall and electronics enclosure. It contains 6 metric pins and 3 M5 fasteners. It also provides a mounting surface for a LED strip. I should mention that this entire machine was printed out of CF-PLA on a bamboo X1C. This material, unlike CF nylon, will tolerate water. It is easy to print, does not warp, and has a crisp, matte appearance. To continue disassembly, we must remove the belts. This is because we must pull the 2 halves of the machine apart. 8 M5 fasteners are used to hold the halves together. A stainless steel endoskeleton provides alignment features and rigidity. There are probably fewer parts on this machine than a typical Voron 3D printer. Each half of the machine is composed of simple 3D prints, alignment pins, and another dozen M5 fasteners. Laying out all of the components is a good visual of this simplicity. I did my best to avoid the need for supports on almost every print. The result is a reasonably dense machine which contains a significant amount of steel by mass. With the concept proven, our next step is to continue to polish the design until release. Our focus is on the hobbyist experience. We want to minimize the time required to set up a cut and maximize the process reliability. On the back of the Powercore, there's a power entry module that will accept both 120 and 220 volts AC, so you can run this off both European and American power. On the front of the Powercore, there are a number of ports. The first port is the output port. This is where the 65 volts DC goes to do our cutting. There's a USB port which allows us to flash firmware to the RP2040 microcontroller inside. There are 2 ports here which allow for closed-loop control of feed rate. One is digital and one is analog. Lastly, there is a safety feature we call the enable port. When you plug in the Powercore, nothing happens until you apply between 5 and 36 volts to this port. Then the Powercore will begin outputting the pulsed 65 volts DC and cutting will begin. If you would like to follow along, there is a link to our Discord in the description. I will be posting updates on my day-to-day work there and on my personal X profile. Here are some of the most frequently asked questions I have received. How fast is wire EDM? The cutting speed of the machine is dependent upon the material thickness and melting point. The thicker the material, the slower it will cut. A 3 mm thick plate of aluminum will cut at a rate of up to 28 millimeters per minute. Steel generally cuts 3 to 4 times slower than aluminum. Titanium is somewhere in between the two. Materials like graphite, which have a very high melting point, machine even slower. The thickest material we have processed thus far on our wire EDM machine is 2-inch thick 6061 aluminum. How long does the wire last? The rate of wire consumption is also tied to material thickness. Expect to use more wire when cutting 2-inch thick metal than 2 mm thick metal. That being said, it approximately takes 12 to 16 hours of machining to generally consume a 250 gram spool of wire, but mileage may vary. You can purchase spools of EDM wire on our website. This wire is zinc coated, meaning that it can machine faster than plain uncoated brass wire. It is also hardened, which allows for easier handling. I would like to thank last year's Kickstarter backers for helping us get off the ground. Last year, we successfully delivered to our backers on time. Since then, we have relocated to Colorado Springs, Colorado, built a shop, and secured investor funding. We are now interested in hiring engineers to begin work on a new class of wire EDM machine for consumers and industry. We are searching for talented and driven electrical engineers, as well as software developers familiar with Vue and Clipper. We also need mechanical engineers and CAD junkies who are interested in mechatronic product design. You will be working on-site to develop next-generation machine tools, such as wire EDM machines. If you have any questions, I will be happy to answer them in the comments.